The first crack, quantum measurement paradox. Start with the slit. You send single electrons, one at a time, through two narrow openings toward a screen. If no one checks which slit each electron chose, the screen builds an interference pattern, bright and dark bands like ripples crossing. But place a detector at the slits to learn which way, and the pattern collapses into two fuzzy blobs. Same electrons, same apparatus, one difference. You asked a question. The result changed. That's not a metaphor. That's the experiment. The stakes are heavy. If outcomes depend on questions, reality waits for instructions. Now scale the question. Wigner's friend turns a lab into a character. Inside a sealed room, a friend measures a quantum system and writes "up" in a notebook. Outside, Wigner treats the whole room, friend, notebook, apparatus, as one quantum state, still in superposition. Both descriptions can't be true in the same way. So when does the measurement happen become a fact? At the click of the detector? When the friend looks? When Wigner learns? If the compile step is delayed, the world holds two versions of events. Somebody's real isn't globally real yet. Wheeler's delayed choice adds a twist. Decide after a photon passes the slits whether to measure its path or its interference, and the outcome still respects your late decision. From our perspective, it's like the system keeps alternatives alive until the very last compatible moment, then writes a single consistent history. That's not retrocausality in the usual sense. It's consistent with quantum rules. But as a story about how realities become real, it reads like just-in-time compilation. Don't render the path until the scene needs the path. Physicists don't shrug at this. They build experiments that push the boundary, weak measurements that barely disturb systems, delayed choice entanglement swapping, where correlations appear between particles that never coexisted, nested interferometers that force you to admit a particle can leave breadcrumbs where it apparently never traveled. Each result lands inside the quantum formalism, but the human questions pile up. Where is the line between possibility and fact? Who draws it and when? There's a pragmatic answer: decoherence. Interactions with the environment entangle the system with countless degrees of freedom. The off-diagonal terms, those delicate superpositions, bleed into surroundings and become effectively unobservable. In practice, that means the world looks classical, because interference between macroscopically different states gets washed away insanely fast. It's the best broom in physics. But it doesn't pick a single outcome. It hides alternatives and correlations we can't access. The paradox doesn't vanish. It becomes a bookkeeping problem. Where is the record of what happened? If you're thinking like a systems engineer, the metaphor is tempting. Measurement is a write to stable storage. Before the write, variables can live in registers, cheap, reversible, superposed. During the write, the system commits to a branch. If the universe is a finite machine, commits might be throttled, batched, or rolled back under load. Labs chasing quantum advantage feel this daily. Qubits are fragile. To measure, you integrate weak signals over time, reject noise, and still risk collapsing states you wanted to keep. It's not mystical, it's cost. Then there's Wigner's friend-style consistency under observers. In a perfectly isolated thought experiment, two observers can assign different states to the same system and both be right within their frame. The consistency constraint is that when they compare notes, outcomes must align. In compute terms, that's eventual consistency. Local views can diverge. Global reconciliation reconciles them, but at a cost in bandwidth and latency. If reconciliation fails, we'd expect contradictions. I saw up, I saw down, both backed by perfect logs. That hasn't happened. The constraint is ironclad, but it raises the resource question. What guarantees the merge? Now bring in the delayed choice experiments that couple light years of path length to a late switch. Signals still respect light speed, but the correlations hang together. No influence crosses faster than C. The global quantum state simply encodes the right constraints from the start. It's elegant, unless you're tracking resources. Encoding those constraints across vast distances without a physical substrate carrying a classical message looks like a pre-computed consistency plan. It's fine if the plan rides on the wave function. It's expensive if you imagine a simulator faking it after the fact. Counterpoints matter. Many World says there's no special compile step, just unitary evolution, branching observers, and local experiences of a single outcome. Bohmian mechanics gives definite particle positions guided by a pilot wave. Objective collapse models bake in a tiny chance of stochastic collapse that scales with mass. Each resolves some discomfort. None removes the empirical core. Outcomes sharpen when measured, and the sharpening obeys rules that treat information as physical. As Rolf Landauer put it, information is physical. You pay to erase a bit. You pay to write one too. Here's the crack then. As experiments scale from single photons to mesoscopic molecules, from tabletop interferometry to satellite tests, keeping superpositions alive gets exponentially harder. That's expected from noise. But watch the pattern. Every time we push the Heisenberg boundary, we're negotiating with a system that resists clean, late writes. If measurement is commit, then high complexity commit should be the first place a finite engine shows strain. That strain wouldn't look like magic. It would look like tiny biases under specific loads, weird but replicable edge case failures, or statistical anomalies that vanish when you reduce complexity. What nobody knew at the time we first drew those interference fringes is how far we could push the compile step before it breaks. We still don't know, but the next clue lives right next to measurement: memory. If measurement writes, where do the writes go, how are they indexed, and what happens when pointers cross scales? Entanglement already hints that memory isn't local. So we go there next. The universe's memory model, error rates, and what it costs to keep the ledger straight. Memory leaks, entanglement, error rates, and quantum limits. Start with the weirdest shared notebook you'll ever meet. Take two photons born together in a crystal. Measure one here, the other across town, and their results line up in ways no local story can explain. That's entanglement. Correlations that don't care about distance, yet never send a usable signal faster than light. Labs prove it daily with loophole-free Bell tests. If measurement is a right, entanglement looks like shared pointers, two variables referencing the same underlying record. Change how you read one, and the joint record constrains the other. Nobody's cheating causality. The correlations are baked into the state. But shared pointers invite bugs. In code, if a pointer outlives what it points to, you get a dangling reference. Physics version: let entangled qubits sit in a messy environment, and decoherent starts chewing through their fidelity. The joint record is still there in principle, but practically it's smeared into the noise of the world. That's why every quantum lab sounds like a reliability engineer. They talk in error rates, T1 and T2 times, leakage out of the computational basis, crosstalk between lines. Keep the qubits cold, shielded, isolated, and they still wander. Errors don't hate us, they just outnumber us. Quantum error correction is the counterspell. You don't trust a single physical qubit. You spread one logical qubit across many, entangle them, and measure stabilizers to detect flips without collapsing the encoded information. It works, but it's brutally expensive. The surface code, today's workhorse, demands thousands of good enough physical qubits to make one robust logical qubit for non-trivial algorithms. And good enough means gate fidelities above tight thresholds and fast, repeated syndrome extraction. Every cycle is a bet that you can catch and fix errors before they pile up. Here's where the universe starts to look like it has a fidelity budget. When we scale devices, we see patterns. Crosstalk grows with wiring density. Noise sources couple in new channels. Control pulses bleed into neighbors. Materials sprout two-level defects that flip with temperature or stress. Superconducting circuits hit one set of walls. Trapped ions hit others. Laser intensity noise. Motional mode crowding. Micromotion. Neutral atoms bring their own gremlins. Spontaneous scattering. Imperfect blockade. Different platforms. Same feeling. The larger the entangled state, the tighter the timing, the thinner the margin. Honestly, it's like hosting a dinner for 4 and 50 cousins show up. Crowded table, spaghetti of cables. Meanwhile, in simple, classical-looking systems, everything's beefy. Your phone's bits are robust. A metal bar remembers its length well enough for engineering. Classical UI tolerates abuse because redundancy is everywhere. Many degrees of freedom average out noise. Error modes get damped. But down where entanglement lives, redundancy cuts both ways. The same coupling that lets you knit qubits into codes also gives the environment 1,000 ways to pull threads loose, so you build more code. That means more qubits, more cycles, more chances to leak. It's a treadmill with physics setting the incline. Physicists map this treadmill in numbers. Coherence times sit at microseconds to seconds, depending on platform. Gate fidelities creep from 99% to 99.9 something. Every extra 9 is expensive. Fault tolerance thresholds promise salvation above a certain line, but they're asymptotic. They tell you scaling is possible, not free. And lurking under the dashboards are non-Markovian tails, memory in the noise. If the errors aren't independent and identically distributed, your fancy thresholds wobble. Nature has a long memory. Materials age. Drifts drift. Now tie that back to entanglement as a memory model. In the fundamental theory, entanglement is the bookkeeping of reality. It tracks who's correlated with whom, so that when you read one log, it's consistent with others. If the universe is finite compute, that bookkeeping might be bounded in practical fidelity. Not a conspiracy, just a cap on how cleanly global constraints can be maintained as systems get larger, colder, and more intricate. If there's a memory leak anywhere, it appears where the ledger is densest. Large-scale entanglement, long baseline correlations, high-depth circuits. We've already seen hints of scaling strain. Multi-atom entangled states, GHZ cats with dozens or hundreds of atoms, fragilize as n grows, phase noise scales with n, and contrast falls. Boson sampling experiments with many indistinguishable photons show output distributions that drift under tiny component imperfections, making certification tricky. Scrambling experiments that measure out-of-time order correlators need exquisite control. Small calibration slips look like physics. None of these are final glitch alarms. They're reminders that pushing entanglement is a fight against an exponential surface area of ways to fail. Quantum error correction tries to buy us headroom, and it works, until overhead eats the budget. Logical cycles grow. Cooling loads rise. Classical side processing for decoding syndromes becomes a bottleneck. You can offload to faster electronics, but then you hit heat and latency. It's turtles all the way down, and every turtle costs watts, bandwidth, and time. In a simulation frame, this is where the analogy sharpens. Sustaining high-fidelity, non-local correlations at scale is the most compute-hungry thing you can ask a universe to do. If a runtime trims load, it trims here first. So what would a real memory leak look like to us? Not Hollywood glitches, no pixels falling off the moon. It would be subtle, targeted, reproducible weirdness in high-complexity quantum tasks, correlated error bursts that don't fit noise models, syndrome patterns that imply impossible coincidences, fidelity plateaus that won't budge past a boundary despite materials and control improvements elsewhere. You'd see anomalies that vanish when simplified. Turn off 3 couplers, shorten the circuit, reduce N, and the ghosts leave. Meanwhile, the classical layer stays smooth because it's cached. Nature's UI pointer states that decohere into redundancy hides small fidelity losses behind consensus. That's the tell. Fragility below, robustness above. If entanglement is our window into the ledger, then its error rates are our first read on the universe's limits. And if those limits bind harder as we scale, the crack we felt at measurement widens into a budget line. A bound on how coherent the world can be, for how long, across how much space. That budget doesn't end the story, it sets up the next one. Because a bound on coherence looks a lot like a bound on detail. And at cosmic scales, bound on detail lives on horizons. Black holes, bit counts, and the strange rule that area, not volume, measures information. If entanglement is the ledger, horizons are the ledger's edge. Now we ask, how many bits fit on a boundary, and what happens when the world tries to write more? Rendering budget, holographic principle, and bit limits. Here's the jump. From fragile qubits on a chip to the hardest cap the universe seems to enforce. How many bits fit on a boundary? Black holes force this on us. Toss matter in, and you'd think its information content should scale with volume. But Jacob Bekenstein did the accounting and found a different rule. The maximum entropy inside a region is proportional to the area of its boundary, measured in Planck units. Then Stephen Hawking gave us a temperature and an evaporation rate, and entropy followed the area law exactly. That's a budget, not a vibe. If entropy is the count of microstates, the number of distinct configurations compatible with what you see, then the area law says, you don't get infinite backstage detail just by stacking stuff inside a region. The boundary, its surface, sets the cap. That's weird until you treat it like storage. Nature doesn't pay for bits in the volume, It pays for bits on the surface that encloses the volume. The Bekenstein bound generalizes this. For any system with energy E in a sphere of radius r, the information content is bounded. Blow past it and you collapse into a black hole, which resets you to the area budget. Leonard Susskind and Gerard Hooft took the hint and said it out loud: holography. A full three-dimensional world can be encoded on a two-dimensional boundary. Not as a trick, literally equivalent physics. The sharpest lab for that idea is AD-SCFT. A gravity theory in a bulk space is exactly dual to a quantum field theory on its boundary with no gravity. Different languages, same story. Calculations done on one side translate to the other, including black hole thermodynamics and quantum entanglement structure. It's a dictionary for how space-time could be a compression of deeper information. Now bring back our runtime metaphor. If the world's detail is capped by surface area, you get a rendering budget. There's only so much state the universe can track inside a region before the boundary saturates. Smooth experiences are still possible, just like a game looks smooth at 60 frames per second, but you can't exceed the memory cap without reducing resolution, culling distant detail, or offloading. Holography says the offload target is the boundary degrees of freedom. The disk is the horizon. Scientists don't all agree on what holography means for our universe because AD-S space-time isn't our cosmology. But the area law keeps showing up. Entanglement entropy between regions and ground states follows area scaling. Quantum error-correcting codes turned out to be the right math to model bulk boundary relations in toy holographic models. You can literally draw a tiling where each boundary tensor stores and protects bulk information in a way that mirrors how error correction works on a chip. Less is more because redundancy lives on the edge. Here's the sticking point. We walk through a world that feels continuous, with insane detail at every glance. How does a capped bit budget produce that? Two moves make it work. First, compression. Physical law is simple and local enough that you don't need to store every pixel. You generate appearances from rules. Second, redundancy. The classical UI repeats the same facts across many degrees of freedom. Your coffee cup's position is encoded in zillions of atoms and in the light bouncing off it. That redundancy makes it feel crisp, even if the underlying ledger uses fewer compressed bits than your eyes think. But compression isn't free. The smoother the fields and the cleaner the symmetries, the cheaper the description. When fields get turbulent when you stack complexity, the compressed description expands. That's a compute tax. If the bit cap is hard, area, and the compression demands spike, the runtime can't just mint new storage in the bulk. It has to shuffle detail to the boundary, drop resolution somewhere, or slow the rate at which new independent detail accrues. From our side, that could look like fewer long-range correlations, harsher decoherence, or hard limits that show up as thresholds we can't cross without gravity answering. Think about cosmic horizons. The observable universe has an apparent boundary. Beyond a certain distance, light hasn't had time to reach us. That boundary comes with an entropy. The Gibbons, Hawking story for de Sitter space ties a temperature and an area to cosmic horizons, echoing black holes. If horizons carry entropy, they carry storage. Then the budget becomes global. As the universe expands, the boundary area changes, and so does the total room for independent detail.